Now that we have a unit tangent vector and a principal unit normal vector, we can start discussing things like the components of acceleration. The unit tangent vector and the principal unit normal vector can actually be used to find the acceleration for an object along a curve. Now that we have a handle on how the direction component of the velocity vector will change, we'll move on to how the velocity vector changes when the speed of the object changes. Once again, capital T is the unit tangent vector, and it gives the direction of motion along a curve at a specific point on the curve. The unit tangent vector is given by the velocity vector divided by the speed. If I rearrange this a little bit, I get the velocity vector is equal to the speed times the unit tangent vector. And since the speed is also given by ds dt, I can write the velocity vector as the unit tangent vector times ds dt. Now, starting with this expression for the velocity and knowing that the acceleration is the derivative of the velocity with respect to t, I simply differentiate both sides with respect to t, and I have to use the product rule on the right. My acceleration vector will be given by the derivative with respect to t of the velocity vector, which is equal to the derivative with respect to t of the unit tangent vector times ds dt plus the unit tangent vector times d2s by dt squared. Using the fact that the chain rule gives me d by dt of the unit tangent vector will be equal to d by ds of the unit tangent vector times ds by dt, I can rewrite my acceleration as the derivative with respect to s of the unit tangent vector times ds dt times ds dt plus the unit tangent vector times d2s dt squared. The first factor in the first term on the right is the derivative with respect to s of the unit tangent vector. That is just kappa times the principal unit normal vector. ds dt is the magnitude of the velocity, so I have two factors of the speed. And d2s by dt squared is the tangential component of the acceleration, which I will label a sub capital T. This allows me to write my acceleration vector as being equal to kappa times the principal unit normal vector times the speed squared plus the tangential component of the acceleration times the unit tangent vector. Now, if I let kappa times the speed squared equal the magnitude of the cross product of the velocity and acceleration divided by the speed, this is equal to a sub capital N. This is the normal component of the acceleration, so that my acceleration vector can now be expressed very concisely as the normal component of the acceleration times the principal unit normal vector plus the tangential component of the acceleration times the unit tangent vector. The tangential component of the acceleration, a sub capital T, is just the standard acceleration that we use for motion along a straight line. It can be also expressed as the second derivative of s with respect to t. This is in the direction of linear motion. The normal component of the acceleration vector a sub capital N, which is equal to kappa times the speed squared, is orthogonal to the tangential component at all points along the curve. This component increases in magnitude as the speed increases and as the curvature kappa tightens. So let's look at an example. I want to find the tangential and normal components of the acceleration for an object moving along the trajectory given by the vector r of t has the components 20 sine t, 20 cosine t, and 30t. r prime of t, which is my velocity, is a vector with components 20 cosine t, minus 20 sine t, and 30. The second derivative of my Trajectory is the acceleration. This is given by a vector with the components negative 20 sine t, negative 20 cosine t, and 0. The normal component of the acceleration, a sub capital N, is equal to the magnitude of the cross product of the acceleration and the velocity divided by the speed. And the tangential component of the acceleration, a sub capital T, is given by the dot product of a and the unit tangent vector. This can be written as the acceleration vector dotted with the velocity vector divided by the speed. I want to actually work smarter and not harder here. If I happen to notice that the dot product of the acceleration and the velocity is equal to 0, I can immediately conclude that my tangential component of the acceleration is going to be equal to 0, and this is going to simplify my work quite a bit. Then if I note that A cross V is equal to negative 600 sine t, 600 cosine t, and negative 400, I can immediately conclude that the normal component of the acceleration is going to be equal to 200 times the square root of 13 over 10 times the square root of 13, or 20. Now that I know the tangential component and the normal component of the acceleration, I can write my acceleration vector, a of t, as a vector with the components negative 20 sine t, negative 20 cosine t, 0, which can be written in very simplified form as 0 times the unit tangent vector plus 20 times the principal unit normal vector. Now you get to try it. Pause the video and find the tangential and normal components of the acceleration for an object moving along the trajectory given by the vector r of t is equal to a vector with the components negative 5, t, and t squared plus 3. When you're ready, restart the video to check your understanding. In order to find the tangential and normal components of the acceleration for this object, I need to find r prime of t and r double prime of t. R prime of t has the components 0, 1, and 2t. R double prime of t has the components 0, 0, and 2. The normal component of the acceleration is given by the magnitude of the cross product of the acceleration and the velocity divided by the speed, and the tangential component of the acceleration is given by the dot product of the acceleration and the unit tangent vector, which can also be written as the dot product of the acceleration and the velocity divided by the speed. A dot v is equal to 0 plus 0 plus 4t. A cross v has the components negative 2, 0, 0. This tells me that the tangential component of the acceleration will be given by 4t divided by the square root of 1 plus 4t squared, and that the normal component of the acceleration will be given by 2 divided by the square root of 1 plus 4t squared. This means that my acceleration vector, a of t, is written in component form as the component vector 0, 0, 2, or I can write it as 4t divided by the square root of 1 plus 4t squared times the unit tangent vector plus 2 over the square root of 1 plus 4t squared times the principal unit normal vector. This is how I can use the unit tangent vector and the principal unit normal vector in order to determine the vector expression for my acceleration in terms of orthogonal components. Be sure and let me know if you have any questions.